So in this video, what I want to do is to consider an example of what's called a reduction formula. So let's start off by looking at the following integral. It's the integral to the sine of x to the power of n, and I'm thinking of n here as being a positive integer. And I'm going to call this integral I sub n, where n is this power here. Now, if I consider this integral, and I use integration by parts on it, and to do that I would write my integrand here as sine to the n minus 1 of x times the sine of x, I can obtain the following result. So I'm not going to obtain it here, we're going to assume that it's true. And if we look at this result, we see here that we have our original integral, which I called I sub n. Here I have some terms which are not inside an integral, and here I have some numbers multiplying an integral of exactly the form that we started with, but with n here replaced by n minus 2 here. So because that's exactly this integral with n replaced by n minus 2, it's very natural to call this I sub n minus 2. So I can actually write out this equation here. I can write this out in the following way. I can say that I sub n, that is the integral I have here, is equal to minus 1 over n sine to the power n minus 1 of x multiplied by the cosine of x plus n minus 1 over n times I sub n minus 2. And this is what I call a reduction formula. It relates an integral, and the integral that it relates is then reduced to another integral with a lower power. And the idea is, by using such formulae, as we're going to see in an example, we can try to reduce a complicated integral eventually to a simpler integral, perhaps having used this formulae repeatedly. So as I say, this is called a reduction formula. So this is exactly the example that I'm going to be using. So on the next slide I'm going to write out this formula again, and we're going to use it to calculate an example. So this is our reduction formula, and the aim whenever we use it is always to reduce a complicated integral something difficult to a simple integral, and by a simple integral I mean something which we can calculate. So that's our aim, and examples of this integral that we might be able to calculate are as follows. So e.g., since we're defining here in to be the integral sine to the power of n of x integrated with respect to x, this means that I1 is the integral of just sine of x with respect to x. N being 1 means here we have just sine of x, and the integral of sine of x is something which is straightforward. It is minus the cosine of x plus, if you wish, an integration constant. And we can see that this is correct because if we differentiate it we get back to the sine of x. And the other case that's also rather straightforward of this one, this particular type of integral, is I sub 0. I sub 0 is the integral of sine to the naught of x with respect to x, and that means it is the integral of 1 with respect to x, and that just means it is equal to x plus, let's be explicit here, an integration constant. So these two integrals, I1 and I0, for this definition are straightforward integrals which we can calculate, and this means that we can use our reduction formula to reduce and reduce and reduce as many times as we need to, and eventually we hope we can get down to this or to this, and to this or to this, and then in that way we'll be able to calculate the integral. So what I want to calculate in this video are the following two cases that I'm going to look at. And the two cases that I'm going to look at are going to be, first of all, I4, in other words the integral of sine to the power of 4 of x with respect to x, and I'm also going to look at I5, which is the integral of sine to the power of 5 of x with respect to x. So those are the two cases. I'm going to look at them in turn, and I'm going to start off with this one. So on the next slide I'm going to again write out our reduction formula, and then we will use it. So this is the example that I want to first calculate, the integral of sine to the power of 4 of x with respect to x, and we want to use this reduction formula here. Let's, before we jump into things, look carefully at our formula. What it does is it reduces in to something plus some numbers times in minus 2. So in this case we're going to go from I4 here, I4, down first of all to I2. The integral of I2 is not completely easy, but then we can use this formula again, and we can go down, if we had 2 here, I2 down to I0, and as we just saw in the previous slide, I0 is extremely easy. So we're going to have to use our reduction formula, and we're going to have to use it twice. So I think there are a couple of other helpful comments. One is that it's useful to use notation like this, I sub n, I sub 4, I sub 2, whatever, rather than writing out the integrals every time explicitly. You know, having a shorthand notation is often very helpful. And the other comment that I think is important is that when we use it, it's important to keep on simplifying, keeping control of the terms that we have, so that we don't end up having lots and lots of nested brackets which we're likely to make mistakes in at the end. So I'll try to clarify that as we go on. So what we now have is the following. I4, so here n is equal to 4 in this formula here, is minus 1/4. I'm just writing out the formula but replacing n by 4, times sine cubed of x multiplied by the cosine of x plus, and now remember n minus 1 is 4 minus 1, so again it's 3, divided by 4 times I2. Now I2 is the integral of sine squared, so replacing 4 here by 2. It's not completely easy, so that means that what we do now is we use the reduction formula again to calculate I2. So rather than writing out a separate equation and then substituting it into here, I'm going to carry on with this equation here and just write out this term explicitly from this. So therefore what we have is the following. I4 is minus 1/4 sine cubed of x times the cosine of x plus 3/4. And now this is multiplying I2, so I'm going to open a big brackets, and now I'm going to work out I2 using this formula here. So I'm going to be saying I2 is minus 1/2 sine of 2 minus 1, so sine to the 1 of x times the cosine of x, plus 2 minus 1, 1 over 2, so a half, times I, 2 minus 2 is 0, so I 0. So let me just do that now explicitly here, remembering that now n is no longer 4, it's 2, because I'm using the formula to calculate this. So we have minus a half sine of x times the cosine of x. I'm not going to write sine to the power 1 of x, that's all that sine of x means, plus 1 half, and then it's I sub 0. So let's now just recall that I0 is just the integral of 1 with respect to x, because sine to the naught is 1, so it is therefore x plus some integration constant. So what we have is that I4 is minus a quarter sine cubed of x times the cosine of x, and now I want to expand this bracket and multiply every term by the 3/4, so it multiplies here and here. So I'm going to get, first of all, minus 3/8 sine of x times the cosine of x plus 3/8 times I0, and I0 we've just said is x, plus some integration constant. So this is our result, and what we can do now is we can check this by differentiating it. So we can check this result by differentiating it, and if we differentiate this, we should get back to our original integrand, and the original integrand is just sine to the 4th of x. So if we differentiate all of this, we should get sine to the 4th of x, and I'll check that on the next slide. So what we've seen on the previous slide, we've calculated this result here, and what we want to do now is to check it by differentiation. In other words, what we want to see is that the derivative with respect to x of I4 is our original integrand. In other words, it is sine to the 4th of x. So let's start off now by differentiating all of this. We're going to have to use the product rule because we have products, and we're also going to have to use the chain rule because here we have sine cubed of x, so this is to a higher power, so we'll use the chain rule, or if you wish to, you can call it the chain rule for powers. So we'll start off using the product rule. We'll differentiate this and then multiply it by the cosine of x. So when we differentiate sine cubed, we bring the 3 down, so we have a minus a quarter. We'll bring the 3 down, we'll reduce the power by 1, so we go from sine cubed to sine squared x, and then we multiply by the derivative of the sine of x, and the derivative of the sine of x is the cosine of x, and then this needs to be multiplied by the cosine outside that's sitting here, so that means that we have cosine squared of x. We then differentiate this, multiply it by all of this, and the derivative of cosine is just minus sine, so we get plus, changing the sign in front immediately, 1/4, and then it's sine cubed of x multiplied by a sine of x, so it becomes sine to the 4th of x. So that's the result that we obtained differentiating this first term. We now move on to this. So for the next term we have minus 3/8, and the derivative of sine is the cosine of x, and that will be multiplied by this cosine here, so we get cosine squared of x, and then we have minus 3/8 sine of x multiplied by the derivative of cosine. The derivative of cosine is minus sine of x, so we can immediately make this plus, and then the sine makes this squared. And then let's not forget we have this 3/8 x at the end. When you differentiate that, we're going to get plus 3/8. So, if we've done everything correct, it must be the case that what we have here is sine to the fourth of x. Now, this term has the right form, but it doesn't have the right coefficient. It's got a coefficient of quarter. We want the coefficient to be 1. So all of these terms have to come together. So it's helpful in such cases to really think about what we're trying to show. And we're trying to show that this is sine to the fourth of x. So that means we don't want cosines. So we can replace cosine squared by 1 minus sine squared. So in other words, we can use our standard result that cos squared x plus sine squared x is equal to 1. So let's now go back to this equation, and what we have is that d by dx of I4 is equal to minus 3/4 sine squared x, and then I'm going to write this cos squared x as brackets 1 minus sine squared x. So this is just this term here. The next term has the right form already, so I'll write that out immediately, plus 1/4 sine to the fourth of x. And now when I look at these terms here, I'm going to leave this term, the sine squared one, so I'll write that immediately as plus 3/8 sine squared x. But this term and this term I'm going to put together because I recognize that this is 3/8 times 1, that's this term here, minus cos squared x. So this term is this, and this term together give me this, and I recognize that 1 minus cos squared x is sine squared x from the standard result. So what I therefore have is that the derivative of our result for the integral is minus 3/4, I'm now expanding these brackets here, minus 3/4 sine squared x plus 3/4 sine to the fourth of x, because I've got sine squared times sine squared, plus 1/4 sine to the fourth of x, and that's very nice because these two terms are going to come together to give us 1 times sine to the fourth of x, which is the result we want. And then here I have 3/8 sine squared x plus 3/8 times sine squared x, so I have twice 3/8, which is 3/4. So I have plus 3/4 sine squared x from this bottom line here. So we see that this term and this term cancel, this term and this term add, so what we have is 3/4 plus 1/4, it's 1 times sine to the fourth of x. So the derivative of our result for the integral is the initial integrand and because we've regained the initial integrand by differentiating our result for the integral, we know that our result for the integral was correct. This result up here is correct. So we've used the reduction formula and now we've differentiated it and shown it's correct. What I want to do on the next slide is just to do one more example of using the reduction formula. So in this slide I want to calculate this example, the integral of sine to the fifth of x with respect to x, again using our reduction formula. And the point I want to make through calculating a second example is that here we're going to reduce down to a different finishing point. So every time we use this reduction formula, n decreases by 2. N goes to n minus 2. So the first time we use it here, I5 will be reduced to I3. I3 is the integral of sine cubed. It's not immediately obvious. But we can then use the integration formula, or reduction formula again, and reduce from I3 down to I1. And I1 is the integral of sine of x, and that is a standard integral which we can do. So in that way we're going to be able, through using our reduction formula just as before, to do the integral. And I'd encourage you now to actually try to do the integral, use the reduction formula, pause the video, and then after you've done that, start the video again and see if you get the result I've got. So perhaps pause now. Okay, welcome back. So what we have is that I5, using our reduction formula with n equals 5, is minus 1/5 sine to the fourth of x times the cosine of x plus 5 minus 1 is 4 over n, which is 5, times I3, 5 minus 2. We use the formula again, but now with n equal to 3. So what we're going to obtain is minus 1/5 sine to the fourth of x times the cosine of x plus 4/5 multiplying into, so I'll open brackets, and it is minus 1/3. Remember, here n is now 3, minus 1/3 sine 3 minus 1 is 2, sine squared of x times the cosine of x, plus 2/3 I1. And we recall that I sub 1 is the integral of sine of x with respect to x, and that is going to be minus the cosine of x, because when you differentiate minus the cosine you obtain the sine, so that means that this is the correct result. So therefore what we have is that I5, the integral we want to calculate, is minus 1/5 sine to the fourth of x, we just have to rewrite this again, times the cosine of x, and then we take the 4/5 and we multiply it into all of this, so here we have minus 4 over 15 sine squared of x times the cosine of x plus 8 over 15 times I1, and I1 is minus the cosine of x, so I'll just write the cosine of x, and I will change this plus sign into a minus sign, and then we can add on an integration constant. And I'm being a little bit sloppy about the notation. The integration constant that I'm writing here is not this one, because this one would be multiplied by the 8/15. So I'm just writing down an integration constant in this formula. So that's our result, and clearly one can now check the result by differentiation, and I'm not going to do that, I'll leave that for you as an exercise. So in this video what we've done is we've looked at examples, or an example of a reduction formula, we've realized that what we do is that it reduces an integral to another integral, and the aim is, by using it perhaps repeatedly, and in this case we've used it every time twice, one can reduce the integral to something which is doable. And in the examples we've looked at, the doable integrals were the integral of sine of x and the integral of 1, both of which were very much integrals which we can straightforwardly perform and know. So with that, I'll stop this video.